You control the settings. Oh yeah, I can do that. You're able to log in copy list? I think it's not on there. It's up. Did we start the recording?
Yeah, already started.
Okay. Okay, sorry for little delay. I got confused and I was in a different room. So anyway, hi, I'm Yano, and today I'm with my colleague Patrick, and we are going to introduce PyTorch XL auto sharding and also its optimization for different hardware backends. And today's session is divided into two parts. The first part would be sort of like a short introduction to PyTorch XL auto sharding, like introduces API, how one can enable this new experimental feature, mostly in PyTorch context. But then the second part we will like dive deep into the XLA auto sharding and how it works, and also touch on like how the cost model for auto sharding can be tuned or optimized for different hardware backends. Okay. And then at the end of the presentation, I will also share some useful reference examples for those who are interested. Okay. Okay, so let's start with the introduction. And in the previous PyTorch XLA release, we've announced GSPMD integration into PyTorch XLA. So to use GSPMD, you basically have to take some PyTorch tensors and annotate it with some sharding specs based on your intention or your thoughts, using this mock sharding annotation API, right? So if you look at that example down there, like we are defining two tensors, T1 and T2, and also some logical mesh shape like 2x4 mesh. And in the red box, we are calling this sharding annotation API to annotate that T1 tensor to be partitioned across the 2x4 logical mesh, right? And if you look at the bottom computation, like simple matmul, T1, T2, and then you get the T3 output, you notice that how we don't need to call all together on T1 or partition T2, actually match the sharding on the T1 to drive that T3 computation. So essentially what GSPMD does, it takes the usual sharding, like partially annotated on some of the tensors in your program, and then convert that your program that is written for single XLA device into a partitioned one now that runs for multiple devices, right? And then this PyTorch XLA sharding annotation API is also integrated into PyTorch's native distributed dtensor API pack. So you can simply call distribute tensor with the XLA device mesh to start using GSPMD. Okay, just to quickly recap and to summarize how GSPMD works, given a user model code, we select maybe a handful of tensors and annotate those with your sharding intentions. Now the compiler takes that sharding annotations and try to infer shardings on the rest of the computation graph and also automatically insert some collective communication ops so that your partition program is semantically identical to the original unpartitioned one, and you get the same result. And one of the, I guess, the key challenges in using GSPMD is actually choosing the right set of tensors to annotate, and also providing, like, I would say, like correct sharding annotations. And that is because if you provide, let's say, suboptimal sharding annotations, then like surprisingly, the final distributed computation result or the performance will be actually not quite good. It could be bad. So you need to have some expertise and also need to iterate, spend some time and put in some efforts to actually get it right. Okay, so that is basically the main problem we are addressing here with the PyTorch XLA auto sharding. So PyTorch XLA auto sharding calls into XLA auto sharding paths, and then the compiler now not just the sharding propagation based on the usual sharding notation, but now solves this optimization problem to actually find the optimal sharding strategies for the entire computation graph, right? And the goal is to provide reasonable out-of-the-box performance for most ML workloads, and of course without any usual sharding annotations. And if you look at the sort of a preliminary test result that we had, at the bottom, like from the left, we tried some popular Hugging Face PyTorch models like GPT-2, Llama, Gemma, and you see that in green, the auto sharding result, the MFU training MFU result actually came out to be comparable, like quite close to our human optimized GSPMD one with the best sharding strategies, sharding annotations. And on the right, we also have auto sharding result for non-transformer based model, like namely stable diffusion. So the original Hugging Face stable diffusion training script, let's say, like runs about like 1 sample per second, and then you run auto sharding like out of the box. Now it starts run much faster because now you are utilizing multiple devices. Again, like you don't have to go through the entire model. You can just treat it as a black box, and it automatically just shards things. Okay, and this all sounds very awesome, right? But then it comes with the cost. There's no free lunch. And one of the things that you need to be aware of is that auto sharding increases the compilation time. So if you look at the bottom plot, the 2 billion parameter GPT-2 model, the normal compilation time without auto sharding pass took, let's say, 1 minute, about 1 minute. But now it jumped to 11 minutes with the auto sharding. And in case of a stable diffusion, the accumulated compilation time jumped to more than 30 minutes. And you can imagine the larger the model actually can take in the orders of like hours, right? So to address this compilation overhead problem, PyTorch XLA currently supports persistent caching, but also we are working on AOT compilation to actually allow the customers or the users to pre-compile from any machine for target topology and then run it later without the compilation overhead. Okay, so how do we enable or use auto sharding in your PyTorch program, right? There are a number of ways. Right now, we do support like 3 different ways to turn this feature on. The first one would be environment variable, where you just set it XLA auto SPMD to 1 and run your training script. Okay, that's yes, that is very straightforward, simple, but we don't want to introduce too many environment variables because over time we forget about them. But the second more programmatic approach would be using PyTorch XLA's SPMD API, like XL use in your code. Right? XL use SPMD, and now we introduce this new Boolean flag, like auto equals true, then it starts automatically partitioning your program. The last and probably the most recommended way going forward would be calling the dtensor API, like discrete module with the partition function. It calls the auto policy that we provide. So this is nice because now the PyTorch users, they stick with the same dtensor API for like CUDA backend and now also for the XLA backend. It's just that the compiler does the partitioning job under the hood for the user, but semantically, hey, discrete module API is supposed to distribute the module. So it achieves that through a different means. Okay. Okay, and then also the auto sharding supports the custom shardings on input data, because the input data is often sharded across the batch dimension for data parallelism. And I think such partition data is often preloaded to devices and asynchronously separate from the main program. and that is better for the performance. So auto sharding or the compiler will respect manually sharded input data and partition the rest of the computation, preserving the user-given input data sharding. Okay, now I will hand it off to Freddy to go deeper and talk about XLA auto sharding.
Thanks, Yunho. Hey all, my name is Prateek. I've been working with Yunho for the past few months to get auto sharding working with PyTorch XLA. And for the next few minutes, I'll be talking about how all of this works internally and sort of what are the next steps or features we are planning with this. So as Yunho described, the entire goal of auto sharding is to have a situation for the end user where the input graph, input HLO graph, and the input module, therefore, has no sharding annotations, can have no sharding annotations. This input HLO will then be ingested by auto sharding. Auto sharding is currently a pass in the XLA compiler. And the output of auto sharding will essentially just be the same HLO, but with every HLO op in that module annotated with a particular sharding annotation. That's essentially what GSPMD does. However, without needing to have any seed starting annotations to start the entire jumpstart the process with. So auto sharding emerged as an open source fork of the Alpha project. This was essentially a research project a few years ago. And the entire approach here enables us to subsume and potentially consider all of these different kinds of common sharding strategies, parallelizing strategies that folks use for large models, right? We can have data parallelism, Megatron, G-shard, the zero optimization strategies. All of these things will be considered by auto sharding as it tries to optimize our input model. Next slide, please. So this slide essentially starts to get into how auto sharding does this, right? So here we have a simple three-dimensional tensor with 3 dimensions S, B, and H. And we want to partition this, say, across 4 devices arranged in a 2x2 mesh, as is shown on the bottom there, right? Now, there's multiple different ways of doing that. You can map different axes of the different dimensions of the tensor to different axes of the device mesh that we have. We can have some axes of the tensors replicated, some sharded over those mesh axes, so on and so forth, right? So there's a lot of different sharding options for a given tensor. And auto sharding will essentially enumerate for every tensor these possible and potential sharding options given an input HLO and a device mesh. And next slide, please. And once it has enumerated all of these strategies, so those are the partition strategies for the operators that you see on the upper left on the slide. Once that is done, it will then move on to computing resharding costs for all of these strategies between producer-consumer tensor, producer-consumer ops in the entire graph. Essentially, depending on what strategy is chosen for each op, there will be a different communication and computation cost associated with that choice of strategies. And once we have this problem formulated, we just feed this into an ILP solver and essentially ask it to minimize this cost, the cost of compute as well as the cost of communication, subject to the memory constraint that the peak memory of the program never go beyond a certain memory budget, right? We want to make sure that our programs don't go out of memory downstream in the compiler, essentially.
So that node cost, you're applying operator communication cost. So what is the communication cost inside the node cost? Won't it be the edge cost only?
Depending on how you shard certain operators, we can have communication within the computation of that operator. So consider a dot operation.
But won't that be included in the edge cost? Won't the communication cost, like you have a separate?
Yes, so the edge costs are only for resharding tensors. However, if, for example, auto sharding decides to shard the inputs to a dot and partition them across the contraction dimension, the dot will have to perform an all reduce. And so you need to compute the all reduce as part of the dot computation and not necessarily because you're resharding a certain tensor. So those are the costs that will go into the node costs. Yeah.
So is the cost of communication and the compute, is it device dependent? Like how can you generalize this, or do you need to feed in some data?
Yeah, so the communication costs are device dependent. I'll go in a little bit into that a few slides later. Yeah. All right. Yeah. So like I was saying, auto sharding will essentially formulate this problem, feed that to an ILP solver, and get a solution back. Now, the interesting thing here is that typical model HLOs, and today we are all interested in LLMs. LLM HLOs often have thousands to tens of thousands of HLO ops. And each of these individual HLO ops will have tens of partition strategies for them, which means that the generated ILP problems are often extremely large and contains hundreds of thousands of variables and edges in the generated problem graph. And so all I'm really trying to say here is that this is really a hard problem with a very large search space. So there are a few tricks that and a few places where we use domain-specific knowledge to sort of try to reduce this problem and reduce the amount of time the solver takes as it goes about optimizing this. Next slide, please. So this essentially just emphasizes the fact that these search spaces are really, really large, right? So even if you consider that simple example of just a small HLO with 256 instructions, each HLO has 2 sharding strategies, you have 2 power 256 options right there, right? That's very large. Now, as I said, we use an ILP solver. Specifically, we use the CPSAT solver that the OR Tools team at Google also releases open source, I think. And the solver is pretty good, right? It uses a lot of fancy techniques to prune these search spaces, get rid of symmetries, do branch and bound, things like that to prune away not promising regions of the search space and so on and so forth. However, as I said, these models are really large. And so we have observed auto sharding to take several minutes to even hours of runtime for some large models. Next slide, please. So as I said, we use a lot of domain-specific strategies, domain-specific knowledge to try to prune this search space. And one very simple strategy that we do, this is not the only thing we do, but one very simple thing we do is to have certain simple HLO ops follow the strategies of their operands, right? This is fairly intuitive. If we have a element-wise operator, we would ideally like for its inputs and outputs to have the same sharding strategies, that they be sharded similar so that you don't have communication in such simple ops, right? This is similar to essentially how we fuse element-wise ops to say dots or convolutions or multiple element-wise ops together. And so essentially we can use that knowledge to tell the solver to essentially group these nodes together and prune the search space that way, because this way what we're essentially doing is reducing the search space and pruning it away for most element-wise ops, most reshape reduction ops in your module, which leads to a significant reduction in the search space. And so this is just one example of the kinds of optimizations we do to get this thing to work fast. So going a bit more into detail about the cost model that we used. There was a question about sort of how we can generalize this cost model and what this looks like for different sorts of hardware backends that users of XLA might be interested in using. So today, auto sharding's hardware specificity in some sense is encapsulated in what we are calling the cost model. And most of this goes into estimating communication costs, which, except for a few cases that I mentioned before, for example, like the all reduce case that I mentioned before, most communication costs are involved when you try to compute resharding costs for a given tensor, right? What would it take to fully replicate this tensor, given that it is currently sharded, and so on and so forth. And to do that, we currently use a fairly simple cost model. This is commonly known as an alpha beta latency bandwidth cost model, where the cost of sending B bytes between a certain pair of devices is essentially estimated to be alpha plus beta into n, right? So alpha can stand in for some latency and beta can be a stand in for your bandwidth essentially. And because we encapsulate our cost model into these two fairly simple constants, and because most devices are often arranged in similar hierarchical, uh, you know, uh, strategies, this cost model can be fairly easily tuned for different kinds of accelerators. Next slide, please. So that's essentially what we want to highlight here. So this slide essentially goes into how we think this could work. One thing I want to emphasize is that we currently don't have the API support for generating a cost model for the new hardware and actually using it currently built in. But we are working towards that, right? So a simple way one could go about doing this is to essentially say we have a new hardware that we just installed, just run inbuilt script that PyTorch XLA would come built in with. It'll generate a cost model by running some simple collective ops, fitting a regression model, so on and so forth. And then we can use that cost model anytime we want to shard a new model on that particular hardware, right? As I mentioned, this is something that we are actively working towards building, and please look out for this in the next releases as we keep building towards this. All right, yeah, so I want to quickly go a little bit into some of the new directions or some of the directions where we are planning to take this project, and some of our next focus areas where we think we really need to make this more robust and featureful. The first thing is that we want to support this on multi-host on cloud TPU, right? As you may have noticed, we are currently releasing this experimental feature only in a single host capacity. And we are actively working towards making it multi-host as well, and scaling it and so on and so forth. As I mentioned before, we are also actively working towards supporting this on other XLA backends, such as GPUs and so on and so forth. This currently works for TPUs internally. And this sort of goes hand in hand with the customization of the cost model and also potentially modeling a downstream compiler optimization so that auto sharding knows the right thing to do for different hardware backends and so on and so forth. Another big thing that we are working on optimizing is the solver runtimes. As Yunho mentioned, auto sharding does lead to a slowdown in compilation, and in a lot of cases that may not be desirable, right? Sometimes we just want a sharding strategy that works really fast because we are debugging something, for example. And so we are actively working to get the solver runtime down. We have a lot of ideas that we are exploring. Yeah, so that would be the end of our talk. We have a few references here, specifically the Alpha project that you can go check out, which auto sharding is based on. They'll give you more details about how things work internally. There's the website's open source, the paper's open source. You can all go look at it. And yeah, we'll take questions now.
Question.
Yep.
Is there support for adding operator level cost? Because like on our hardware type, one of the issues we have found with the SPNB partitioner is that we don't have a performant dynamic slice in every case.
Mm-hmm.
So we then have to modify the partitioner to generate the dynamic slice for our case, etc. So adding in a cost model for the HL opcode would help us. Is that added or?
We currently don't have support for that, but adding that should not be difficult at all. And if there is interest, we can definitely look into that.
Okay.
Yeah.
My other question is the solver. Can you set a timeout for the solver? So it only, and then if you set that timeout, does it prioritize like differently? Like it explores branches that it already thinks will be good. Does it already do that?
Yes and no. We can set a timeout for the solver today, and as long as the solver can find a feasible solution within that timeout, it will return that solution and go with it. That again doesn't mean that it'll be the optimal solution for that cost model, but yeah, as long as it has some solution, we'll run with it.
So in the original paper, they had a heuristic, the GSPMD paper. So is it based on that kind of a methodology, or is it completely different way of sharding? I mean, their paper, they kind of go through a sharding, see if it's heuristics basically. Pick a heuristic, see how it is, and then you kind of iterate on the heuristic.
Yeah.
Right? Is it like that, or is it like you kind of start off with all different strategies and you kind of
It's more the second approach. It's not based on, I mean, we will enumerate strategies for every op, and we will consider all of those strategies. So in that sense, it considers a lot more of the search space than GSPMD would. For example, GSPMD is not a search algorithm. It'll start with some seeds and propagate it based on heuristic rules for every op. That being said, there are still heuristics that creep in elsewhere in the past. So I won't deny that there are no heuristics, but we do consider a lot more of the search space.
And I think it's kind of important to point out that the auto sharding solves the search problem for sharding annotations, but then also the normal SPMD passes that happen. It doesn't replace SPMD, but it runs before and then SPMD still runs. So the heuristics maybe you were thinking of, they still happens. And sometimes it has to rely on the sharding propagation.
I have a couple of questions. So the first one being related to the export of an NN module that contains these user-defined sharding annotations. So let's say I want to mark an arbitrary tensor in my model as being sharded, and I just do a torch.export on that module. I find that Torch Dynamo is not able to trace through these annotations, and it just kind of errors out. And I was wondering if that's possible at all, and whether it's only possible to provide these user annotations at the boundary of the module, and it only gets propagated in either direction from there.
Okay. Jack, should
So I think today the sharding annotation is a thing that live inside PyTorch X-ray. So the torch export itself, but what torch export is a FX graph. That just currently that's not a good way to representing a sharding annotation in the FX graph. So to answer your question, yes, today I think torch export couldn't export a graph that was sharding annotation. Could it be possible? Maybe, but we need to work with PyTorch to actually introduce the metadata that was representing the sharding annotation, whether string or something. And then downstream, we want to consume that graph. We need to be able to consume the metadata and replay the sharding on the tensor. Is it possible? It's possible, but we actually currently don't plan. So if that's something that interests you, feel free to open IFC in PyTorch X-ray. Then we can talk with upstream to see what we can do.
Okay. I mean, so the little experimentation that I've done so far, it's just, I mean, if I have a module, I just mark the input to that module as with some sharding annotations, and then running SPMD eventually, it kind of propagates that annotation through the module into all the computations that I have in my graph.
Right. So actually there are two parts. So there are two kinds of sharding, right? So the one kind of sharding is you sharding on the graph input, the parameter per se. And there's different part, there's activation sharding. Today we actually it's a way for us to actually so there is a way to capture the activation sharding in the FX graph. So we have a custom op that kind of represent the sharding, so that will be captured as part of FX graph. So what we do today when we're trying to inference, not necessarily export, just using torch.compile, it's like we first shard off the input parameter, and then within the model code, we use this custom op to mark the activation sharding. So when torch.compile runs, it will return you FX graph that includes the activation sharding, and then you pass your parameter, which is already sharded. Then that's how we actually do the SPMD plus the torch.compile today. Take a step back. Is it possible we also include the parameter sharding as a custom op? Yes, I guess we just haven't been doing it because we haven't really needed. We can talk more if that's something that interests you. I think it's that way to make it work, but it's not very well defined now.
Okay, and another question I had was how well defined / functional is SPMD support with quantization?
That part I actually don't know, but I do wonder, in my understanding, quantization, it doesn't really torch, like it does convert some operation from the float to the integer.
Right.
But from HLO perspective, it is just a different HLO. So I think all of the sharding propagation should just work.
It actually loses the analysis. So let's say if I export my module to stable HLO,
Sure.
and let's say the initial stable HLO contains these sharding annotations,
Right.
and then I lower the stable HLO to HLO to run the HLO optimization
Sure.
process, which includes SVMD. In the middle of that process, the sharding annotations are lost. So
In which step was it lost when converting stable HLO to HLO?
no, so I go from stable HLO to MHLO first, and then so the initial MHLO still has the quantized types and everything,
Right.
and then I have to convert it to not used quantized types. So basically, break the operations into primitive operations like rounding, multiplication with the scale, so on and so forth. And during that process, the sharding annotations get lost.
I think it's worth filing an issue
Okay.
project
Okay.
because I am pretty sure that quantization works with the SPMD.
Mm.
But in your case, it's losing that annotation while you're converting to stable HLO.
While I lower to HLO.
HLO.
Yeah.
So there is a pass at the end of the SPMD partitioner where it clears sharding annotations. It's in the SPMD pipeline.
No, this happens way before SPMD. So while I'm just converting my stable HLO to HLO, in the middle of just
I see. So
Yeah.
you never reached the partitioner.
right, correct.
How did you, which API did you use to convert stable HLO to HLO?
I just run the passes. So I use MLIR HLO opt. So I first convert from stable HLO to MHLO.
Yeah, it sounds like a problem. Like in that pass, it dropped the sharding annotation somehow. So maybe that's a Kevin problem. I will see where I can
Yeah.
find Kevin offline.
And it might be because you're involving MHLO. Maybe that pipeline.
But is there another way to go from stable HLO to HLO directly without having to go through MHLO?
We don't necessarily go to MHLO.
I think the use case was different. Like for PyTorch, so we generate HLO directly and we provide pass to the stable HLO. But I think your use case, you generate stable HLO
Correct,
first, then
yes.
apply sharding annotation, convert that to the HLO, and something wrong happen in between.
Yes.
I guess it's
I'm sorry, I might have missed some of the discussion, but how do you generate a stable HLO in the first place?
Just using Torch XLA export. So I have my NN module. I just export it using Torch XLA, and then just convert it to.
Give them a better API to not do like two extra unnecessary.
Would it be fine if you just touch export the HLO directly, or you need it to be stable HLO because you want to do some optimization?
Yeah, so we have a kind of compile pipeline that consumes stable HLO. Yeah.
Yeah, I think the problem happened when you're converting from stable HLO back to the HLO.
Mhm.
The sharding annotation was lost. I will see where I can find Kevin.
Okay.
Go HLO to MHLO. Not HLO, because we can do that. Yeah.
Thanks.
Sounds good. Thank you.
I got another question. So for the cost model, you have cost model for the operators and communication, right? Do you consider the communication overlaps?
Currently we do not.
Question.
Currently we do not. That goes more into some of the, as I mentioned, right, that there are opportunities to improve the cost model to further model what the compiler does to the HLO downstream, right? Some optimizations, so on and so forth. Overlaps are one of the things that we want to consider. One of the ways that we can go about doing that, for example, is instead of so today in the problem that we formulate, we minimize the total cost of the entire module, right? We can add another term to that cost, which essentially tries to minimize the longest computation path in some sense in the graph, the depth of the computation in some sense, to reduce to essentially try to get as much model overlap as possible. That's one easy way of thinking of trying to do that, but that is one of the things we want to work on. Yes.
Question.
Yeah.
This is kind of random. Why does the SPMD partitioner never create reduced scatters? It makes all reduced dynamic slice pattern. So like GPU and our HLO pipeline, we always will then make that into reduced scatter, but I never see it making reduced scatter from the start. And I've just wondered why.
I am not sure. I don't
Did
know.
you try to, let's say, partition. Did you partition like contracting dimension?
Yes, and then we cancel that pattern into reduce scatter in a different pass after the partitioner. But I'm just wondering, why doesn't the partitioner create reduced scatters from the start? Because I see XLA GPU doing the same thing. It also makes that pattern into reduce scatter.
So I'm not sort of sure, but then you say that after a different optimization path, it does happen, but it's just that after
If
the partition
For our hardware backend, we add that pass. I'm saying
By
Our-
default, it
for-
doesn't do it.
correct, and I'm just wondering like why it never. And I've seen others talk about it on XLA GPU. I'm just curious why it doesn't.
I am not aware of this. Reduced scatter, it should be very common, right?
Yeah.
Yeah.
Yeah, I would also not, I'm also not the right person to
Okay.
talk to.
So is it because the cost of dynamic slice is very low on your hardware that you don't really care?
This is for manual.
Yeah, on your platform that you really don't
Yeah,
care,
we
to
don't
optimize
run
that. For,
this issue. This is the first time I'm hearing this. So, but I think we mostly work on TPU, so
Okay, sure.
could be.
could be because you never had
Yeah,
to.
that could be, yeah.
I mean, if this
Something
was
that
an issue,
escaped.
like we must have.
Yeah,
prepared.
it's something that just escaped because we never thought. Yeah, it's likely.
Yes.
So you never really take care of tuning for dynamic slices. You just let the compiler do whatever code it. You never took care to see if they're in dynamic slices.
I have not
manually.
I have not
Inject.
ever worried about a dynamic
Slice.
slice, I think. Yeah.
I have one more
That's
question.
interesting.
This is also more on the partitioner.
Mhm.
Why does the partitioner have certain hard-coded strategies, like for gather scatter ops? On current OpenXLA, it's hard-coded to do an index parallel strategy, which is not performant on Neuron hardware because our all-to-all is pretty slow. So we currently subclass that and use vocab parallel. I found that case, and there's another case where if you have a sharding like 418 and you do a reshape, you add a dimension, the partitioner is hard-coded to split sharding, so it'll be 2218. That also isn't good for a lot of our cases. But I guess why are these decisions like explicitly hard-coded in the partitioner?
I don't know. If I were to guess, it same reason is what I would guess, but I'm not sure.
My guess. Another way to put it, domain-specific heuristics
For TPU?
baked in for TPU.
Yeah, that's what I would guess,
Okay.
but again, I don't know.
Yeah.
Okay.
But that's pretty
I
interesting.
think these are all the questions we should delegate to XLA GPU team. They could benefit.
Yeah, I think the partitioner folks would also definitely want to hear about this. Yeah, should note this down. Please.
Do we have anyone from XLA GPU team here? This is a question I can't answer, but I can find someone. Should you know about this? So should we get?
George is downstairs. I
know these sharding specifics. I can.
oh yeah. Yeah, I can look at
I'll work on finding someone.
Okay. Cool. Thank you. I
Maybe-
think
Yeah, I don't know. Maybe Birkin might be a good person in the afternoon.
And Birkin will be there in the afternoon during the lab sessions, so maybe we could.
Yeah, he's on the round table.
Yeah, he is.
Yeah, maybe.
Okay.
Yeah, even Andy, anyone in the compiler team.
Yeah.
I think would be a good person.
okay.
I got another question. So you guys introduce SPMDs. Like, do you guys planning to support MPMD in the future, or like pipeline parallel for specific?
Do you want to?
I mean, I only know, I heard of a plan. There's a parallelization pipeline for MPMD. Also, some that pipeline.
Yeah, I know
don't know if
PyTorch.
they
I know
do
PyTorch does do MPMD. I don't know what PyTorch XLA plans are to use or to integrate with PyTorch. but-
I guess the term MPMD is a bit less well defined. So what exactly is MPMD? So I mean, technically on PyTorch today, like you spawn a bunch of process per device, and each device is doing its own thing. So you can say FSDP, DDP, layer, MPMD. But SPMD, when we say SPMD, we usually refer to GSPMD, like the compiler path. So are you asking for will there be a similar MPMD path in the X-ray compiler that doing things like pipeline parallelism?
Or just specifically pipelining, I think.
I think just pipeline.
pipeline.
Specifically.
So I guess there are two parts. I think X-ray is is making like they have some plan-based thing I know to better support pipeline parallelism. But outside of the compiler world, like PyTorch itself is trying to do pipeline parallelism on a framework level. So technically, you can either use the thing like PP, I think that's how they call it. Like in the framework level, that's going to partition your graph into different pipeline stage and start from there. Or if you want to rely on the stuff, if you want to have a more like similar experience like SPMD, you only provide some annotation, and the X-ray compiler will shard and like the partition the stage for you. I think that's thing. I heard that's a plan, but I don't have a concrete timeline. On the PyTorch X-ray side, I think the more immediate solution is people actually want to do pipeline parallelism is like using the framework level like pipeline stage.
I think in some sort it's like the same problem doing sharding. You see for PP you also need cost models to do the PP, right?
Yeah, but like that happens in a framework level and that's a separate effort.
Yeah, I got another question, probably also related to the cost model. Do you guys try to have recompute plans for the backward, like how to choose the recompute?
You mean like rematerialization and things like that?
Well, for example, you may have like insert all gatherers and in backward reduce scatter, and when you try for the backward, sometimes you want to recompute those new added ops, right? The communication ops. How do you guys choose to
consider this?
the recompute?
So, but then I also curious, auto sharding doesn't consider this, right? This
Auto
is
sharding will
like a framework level.
as long as the HLO module contains these computations, auto sharding will take care of it. I'm not sure if PyTorch XLA.
We do.
Yeah, so then this will be taken care of.
So this, yeah.
So I guess the thing you probably are you talking about the what's the thing called addition checkpointing, like stuff like you drop some of the stuff in the forward and recompute like in the backward.
Yeah, something like that.
Well, I guess like let me take a different angle. From the auto sharding perspective, it doesn't really care is it forward or is it backward. All it sees is the H low with some compute op and some communication op. It just applies cost model.
Wait, so the SPMD is after the autograph.
Oh, well, yeah. So first in the framework level, you run a forward and you run a backward and optimizer, then you generate the HLO graph, and then the HLO graph was passed to the compiler to apply all the sharding paths. Compiler doesn't really care is it forward or backward.
I think maybe another possibly useful response to your question would be like in PyTorch XLA and in that framework level, we do have an option to enable like gradient checkpointing, which forces like material.
It's not really exactly the checkpointing. It's the like recompute op for backward.
Right. So
it's like before, like sometimes you insert new ops in your sharding, right? And then some ops coming out, you want to be recompute in the backward.
Recompute. So gradient checkpointing. Not okay. Yes, we do have an option, but once we enable that, that will be part of the HLO that we pass to the compiler.
Okay.
I guess different things like framework, you can do whatever you want, insert, but then you will generate different HLO. Whenever you generate different HLO, the auto sharding need to rerun. So it's not like I do this and I turn this flag. The auto sharding will magically knows I only do X, Y, and Z. Actually recompute everything, so it's actually going to be slow. So it's better you just figure out what you want to do, generate an HLO, and try to stick with the same HLO.
Okay.
Questions? So in the long term, do you guys see this as like the de facto SPMD as the right now? What's the thinking? Like you want to make this as the mainstream, the SPMD as the mainstream, Jack, and like.
We don't really force our user, like we only provide a recommendation. So I think SPMD is better in a way, actually reduce the compilation time, because in the traditional PyTorch distributed training, you have multiple process you have one process per device. Then each of them need to compile its individual graphs, so compilation time is usually longer. And just in general, SPMD will support an X-ray layer. And we do recommend a new user when it coming for recommendation, how do I train? Like we recommend use SPMD. Our Llama 2, Llama 3 experiment, like of data we publish was with SPMD, but we don't control what people use. We try to support whatever they want to do.
Just to like add to that, I mean, if you ask about the auto sharding, it's the de facto approach report. I think auto sharding doesn't provide really the optimal sharding annotations strategy, right? And the goal is just provide the reasonable out of the box of the comparable performance to the human optimized sharding strategies, along with other like XLA optimization, like flags and settings and gradient checkpointing, so on and so forth. So this is something that is useful for people to quickly try out and see what their performance might be using GSP setup. But if you really want to push the envelope, like achieve the maximum, let's say, latency with the throughput for inference and the MFU for training, then you need to actually spend some time. Yeah, like so, it just targets a different segment.
Yeah.
Of, yes.
Because the reason I brought it up was the compilation time. And I think the morning talk also was mentioned, right? So it bites everybody, right? The compilation time.
Exactly. But
So,
the compilation overhead can be addressed easily. Like we're working on compilation.
Yeah, we do want to reduce that.
Yeah.
Again, because as Yuno said, right, the goal is to just come up with a sharding that works reasonably. And so a use case is that you quickly want to try out something. So that is something that we are thinking about.
Yeah,
Yes.
and then Jack and Shine can attest to this too. Like for really achieve the best performance, let's say on Llama with using GSPMD, a lot of work has been done on like replacing some PyTorch op that is less well supported in PyTorch. So like you need to actually do extra work. It's not always just about the sharding annotation.
the linear layer.
Yeah, exactly. Yeah. And sharding annotations, if you have people with experiences and expertise, you already kind of know what is the best practice. And right nowadays, most of the models have a similar architecture. So I think another interesting example is stable diffusion. Like this is something that we didn't spend time before, but we didn't have a good idea how to shard this properly. So just ran this auto sharding, and it worked to some extent, but we don't know how good it was compared to the best achievable.
Yeah. If it works and if it's reasonable, that
It's
should
a
be
reasonable
definitely
starting
a
point,
success. Reasonable.
Start with this and then optimize further.
The good solution is stops.
So I guess a smart user could look at the HLO dump after auto sharding and then look at the sharding in the metadata. And then if they see something they don't like, they could annotate all the tensors to match the sharding metadata of that intermediate HLO.
Yeah.
And then they get the free, kind of a free, really good starting point.
Yes.
From the 10.
Yes. And you can also iterate with auto sharding, right? Like GSPMD preserves already existing user applications. Auto sharding will also do that.
Do you know if any other hardware vendors are using it besides TPU?
No, not that I know of.
Okay.
Not that I know of. Not that I know of.
Because that'll be the first time another hardware vendor tries to plug in their own cost model, which is what we're looking to do.
Yeah.
But not there yet.
I have a question. So how different is Chardonnay supposed to be from this? Is it meant to be like another tool that's used for this? Is it meant to be a replacement? How mature is it at this point? Yeah.
I cannot answer how mature Chardonnay is at this point. I think there's like Chardonnay folks around that maybe can. But as far as I understand, Chardonnay is beyond just how you shard, which is a lot of what the talk at least today was. Chardonnay also is a lot of how you represent shardings, the APIs and all of that. Today we have a few solutions for sharding already, right? We have GSPMD, we have PartIR spoken about this, XLA auto sharding. And so Chardonnay sort of tries to bring them together, and as I understand it.
In the work on Chardonnay is all the investigation work and development work that happened on the XLA auto partitioning going to go inside as an implementation for it as well?
That is my understanding, but again,
Yeah.
But this work doesn't use that one that you're showing.
This is alpha base. Yeah.
Oh, so it's not doesn't use the
Yeah.
sharding. It doesn't. Okay.
So, but then it's not on the roadmap to actually combine alpha with Pattaya. It will be a separate thing, but then for the
yeah,
auto
by
machine-
unify, I don't mean unify as one product.
unified
Uh,
API.
Unify the API and all of those.
Or
Yeah.
at least the underlying implementation of how you shard things, I would assume that it's shared. It's just the representation that's different.
But that representation enables different features.
Okay.
Yeah, they emphasize on the importance of bringing in the priorities, right? And then SPMD.
So just to make sure I understand. So that means that, for example, the work you're doing on GSPMD now is not like having that work as, you know, implementation of Chardonnay algorithm is not a primary goal, at least for Chardonnay. So today is not the plan to necessarily have all this work that happened on GSPMD back the Chardonnay, right? Implementation.
Don't know what the OpenXLA plans are to that respect. I can't answer. Yeah.
My very shallow, I mean, based on my shallow understanding from the framework's perspective, Chardonnay is just unified API that sits on top of XLA. Maybe it's not going to be inside XLA, but then that will enable us as a framework to actually tap on different auto sharding algorithms or more advanced sharding, like partitioning algorithms, but through the same API. Like right now, we are going directly to, let's say, the XLA API to use GSPMD and also to use auto sharding, but maybe we will go to like Chardonnay API for more advanced stuff, right? Pick and choose.
Okay.
think we are at time.
Did you also fill out the session survey, the tutorial survey? It's in your know before you go. It'll only take like 2 minutes. It's 3 questions. Thank you. And then we'll take a short coffee break. And then you'll go to your next one and we'll start that one around 10:40, 10:45.
Okay, the next one is also this one.
Yeah, so you're doing another session in the same room. Yeah, exactly.
That'll be a survey. Thank you.
Yeah, so you don't have to move. You're good. Unless you want to get coffee too.
I will get.
And the lattes have the little OpenXLA logo on it. So if you guys want to get a latte.
Saw that. That's pretty cool.
Sure.
So there's
Perfect. Awesome.
Yeah, I think people might have gone through the original one.
I went to the list of prints and there was nobody, so maybe
Yeah,
what?
there's a hardware upgrade.
Yeah, where's the third guy?
Like if you can do it, everyone cares about the export side, but
What's the legacy?
MLIR would be great. Yeah, then the question is what the algorithms
Ported over, it's not just going to be used as they are.
Yeah, because
Here it is.
yeah, it's not
Tutorial.
sufficient, right? Like
Yes.
it's a great step,
Yes.
but it's not sufficient to do
Just
the
need to be-
innovation.
Okay, good.
But at this point, I think the good thing is first step. Extremely, I don't think. There's no.
You want to make sure they're all.
I'm gonna go with that XLA optimizing performance and collective.
The only thing that they have
That one was pretty good.
Yeah, but it doesn't integrate.
Yeah.
And you can't extract it.
So much fun.
No, it's
I have to spend some time experimenting with you.
afternoon when you have
Yeah.
to rotate around and just
About-
talk to people.
Yeah.
It's better than like having someone talk at you, I feel like.
Yeah.
Because it's like more relevant to what you need.
Tree.
We get to share knowledge.
Exactly.
You know,
Yeah.
there was
That's
this
a
hope
really
like, oh, okay, we just
Oh.
like, it just happens, and we have to
There you go.
See?
That's right. That's right. I like it. I like it.
have to do something. So, yeah.
Did you guys fill out the surveys?
Oh, yeah, I was just gonna.
I just opened it.
Yeah.
Okay. I just want to give you your t-shirts. That's why I'm like itching to
have
give
to
you
do that.
t-shirts. And the survey's like the little carrot that gets you to fill out.
So, okay. It's in the mail, right? The link.
The know before you go. Yeah, exactly. If you click on the know before you go, you'll see it. There's a link for the tutorials.
And also there are this yes. Session will repeat
Take a, there's a little, we're just taking a little coffee break.
Oh, shit.
So if you want to get a little coffee or something, the coffee, the cafe latte ones, they have the little OpenXLA logo up on top. Yeah, you should take a picture of it because it's so cool.
Great marketing.
I know, exactly.
Hey,
I've already been doing that.
No,
Italian friend, our Italian guy is like, oh, the coffee is good and it looks awesome.
and tweet it out, like hashtag OpenXLA. That's what we have to step and repeat, like the Academy Awards. Did you see that with the carpet?
I didn't pay attention.
Oh, that's where in the lobby, so you can take a picture.
I didn't see.
Did you fill out your tutorial survey for from the last session? Okay, perfect.
so where is the coffee shop you said?
It's downstairs. I think we'll all, I'll take you all down there. Yes, yeah, exactly.
I'm waiting for her.
Okay.
Just a sec. I'm unable to log into my Gmail.
We do it after then.
Yeah, okay.
Yeah.
And let's get a picture of you with the 702. Where did you all come from? Oh, that's awesome. Oh, okay. That's what you do. Okay, I remember the call. Oh, yeah, we're gonna special people. They're like set up. They. Okay.
something back there. I didn't reply to you.
Look at this.
Nice.
Ooh.
There's no one.
I think everybody might have just showed up in the morning session.
Yeah, I think they probably will just.
That would be, I would
In
be
that
happy.
case, we just tell our beloved colleagues that the recording will be available.
Is it available? Did someone record?
Yeah.
Okay,
the
good.
previous session.
I think most people will just hang out downstairs because it was an intense session. It's
know.
1 hour each.
Yeah.
Maybe we can also just take.
The torch export.
Oh, we do have someone joining remotely.
Ah. Okay. But I know Aditi. Aditi is the coordinating this whole event.
Okay.
Um,
Okay, I guess we can just hang out a bit
Yeah.
until like
Yes,
someone
okay.
yeah, I'm gonna just wait.
Google sent me a message saying like the glass breaking heard in my house. What the fuck is happening?
What? Oh my goodness.
That doesn't sound good.
That sounds terrible.
So you don't know what you're going to be working on in the new.
Yeah, yeah. I
Okay.
mean, I will try to
Hey, Suyuan, FYI, like we had the first session that's pretty intense, and then it seems that everyone was just taking a break, so no one's here. We're just hanging out. It's fine. He will get it.
That's a
Okay, I guess we can get started and have more people join in, come into the room if they may. But yeah, so hi everyone, I'm Yano and I'm with my colleague Pratik, and we'll be giving PyTorch XLA auto sharding intro and how this can be optimized for your different hardware backends. So this tutorial session is structured so that we start with the short introduction to PyTorch XLA auto sharding. And I'm going to introduce the API and how one or anyone can just enable this experimental feature to try out. And then my colleague Parik will go a little deeper explaining how XLA auto sharding works, and also show how we envision the tuning and customization of this auto sharding for different hardware backends. Right? And then in the end, we'll conclude with some to-do items in our scope, and also share some useful example references. Okay, so let's start with the introduction. So in the previous release, PyTorch XLA release, we integrated GSPMD into PyTorch XLA. So to use GSPMD, you have to take torch tensor and annotate it with the sharding annotation API that is highlighted with the red box in the code example there. And just quickly going over these examples, we have two tensors T1 and T2. And also in the middle, we are defining this logical mesh, 2x4 logical mesh, and calling this mark sharding annotation API. So what this API does is that it takes in the tensor you want to annotate and take the logical mesh and also the partition spec. In this case, we want to just evenly partition the tensor across this 2x4 device mesh, and that's it. And afterward, the actual computation at the bottom, like mapmul T3 equals T1 mapmul T2, that will happen exactly the way it is written for single XLA device, but then the execution will happen over multiple devices, in this case, 8 devices, since T1 is partitioned. And also, it is important to note that we are not all gathering. We are not explicitly calling all gather on T1, or no, we are partitioning T2 to actually match the partitioning of T1. And the T3 computation just gets executed in a distributed manner. So what GSPMD does is that it takes this single device program, right? No collective communications, no special distributed PyTorch ops, but just take the original one and then automatically transform this into a partitioned program that runs with the multiple devices, right? And then on the right, I highlighted some PyTorch native distributed APIs, so that to emphasize that this GSPMD can be enabled through the torch distributed tensor API as well. You just call this API with XLA device mesh, then it actually start using GSPMD on XLA backend. Okay, and to summarize how GSPMD works, this is a quick recap. And given a user model code, right, it's written for single device. It's the simple case. You don't have to call any collective communications, and user select a few tensors to annotate, right? The annotation is a way for the users to express their sharding intention, and the compiler takes the sharding annotations and the user model code and start inferring the shardings across for the rest of the computation graphs, right? So that happens, and then compiler also takes care of inserting the collective communications correctly so that the partitioned program runs without error or crashing. And at the same time, the final output of the computation is semantically identical to the one from the unpartitioned program. So GSPMD is great, but one key challenge in using GSPMD is actually selecting the tensors to annotate, and also providing the correct sharding annotations. And because annotating your tensors with the, let's say, suboptimal sharding annotations can actually result in bad performance, right? You want to make sure that you're annotating the right way to get the most out of it. Okay, so the goal of auto sharding is essentially just to address this problem, right? We want to provide the reasonable out-of-the-box performance for most ML workloads without requesting the user sharding annotations, right? Because it can be tricky and it requires expertise and a lot of efforts from the user side. How can we make their life better? And the auto sharding can do exactly that. If you look at our preliminary result, test result at the bottom, like on the left, we used popular Hugging Face transform-based models like GPT-2, Llama, and Gemma to try out auto sharding and compare the result to the human-optimized best result on PyTorch XLA. Right, the blue bar represent the result from using the human-optimized sharding annotations with the GSPMD, and the green bar is the auto sharding result. And I mean the actual MFU numbers for training is maybe hard to read, but then you see that the height they are very close to each other, kind of comparable. So it achieves our goal that we want to provide a reasonable out-of-the-box performance. And also, auto sharding works with non-transformer based model, like Stable Diffusion. If you look at the plot on the right, we used auto sharding on Hugging Face Stable Diffusion training, and the training throughput actually jumped threefold from the original unpartitioned training script throughput. Right. So auto sharding also works with the non-transformer based model, and that was a pleasant surprise for us. Okay, and then as we all know, there's no free lunch. So auto sharding comes with a cost. In this case, the cost is the increased compilation time. As you can imagine, searching for the optimal sharding strategies is actually could be quite expensive, right? It's an expensive search problem, and this reflects on the increased compilation time. In case of a 2 billion parameters GPT-2 model, that's the left side, the bars. The compilation time jumped from 1 minute to 11 minutes. And for Stable Diffusion, again, only the 2 billion parameters, the compilation time jumped to, let's say, 4 minutes to 33 minutes, right? And this actually will run for hours for larger models. So to address this compilation overhead, PyTorch XLA, we support the persistent caching, but we are also working on AOT compilation, so you can pre-compile for any target topology in advance before the execution, before your actual run. So how do we use auto sharding in PyTorch XLA? The most simplest way would be just setting this environment variable, XLA auto SPMD, and then run your training script, and then everything will be automatically sharded. Then I mean it's actually remembering all these options and environment variables could be tricky, and we are very forgetful. So in that case, we also have this programmatic PyTorch XLA SPMD API. So this is use SPMD API. You just pass the auto equals true flag, and it will start partitioning your program for both inference and training. And lastly, we actually recommend using the same PyTorch distributed API for distributed workloads. So in this case, auto sharding is integrated into distributed module API, and we provide partition function for distributed module API, which is called auto policy. And you call distributed module with this auto policy as a partition function, then your module will be automatically partitioned. And auto sharding also works with the input data sharding. So it is often the case that user shard their input data their custom way, right? So oftentimes the batch dimension of the input data is sharded for data parallelism, and such partitioned data will be preloaded to your device in the background and separate from the main program execution. And this is better for the performance. You don't have to wait or block on this data transfer because it already happened or it's happening in the background. So the compiler will actually preserve and respect this custom sharding on input data and try to partition the rest of the computation on top of it. Okay, now I will pass it to Pratik, who will who will help us understand how XLA auto sharding works and also touch on the optimization of the auto sharding cost model.
All right. Thank you, Yunho. My name is Prateek Hayal. I have been working with Yunho for the past several months to get auto sharding working with PyTorch XLA, and now I'll go a little bit into detail about how auto sharding works and how it can actually start with an HLO module and come up with reasonable sharding annotations for those modules. So as Yunho said here, the goal here is still to have a situation where auto sharding ingests an input HLO which has no sharding annotations or which can have no sharding annotations, and auto sharding will do its thing, and we'll go into that, and annotate each and every tensor with a sharding annotation. That's the goal here, and auto sharding achieves this as an XLA pass. So it'll ingest an HLO and output an HLO with the sharding annotations. Next slide. So one thing that I want to point out here is, being a search approach, a search-based or an optimization-based approach, auto sharding has a large search space, and so it can actually subsume a lot of the common sharding partitioning strategies that we use with large models, right? Things like simple data parallelism or Megatron or G-shard MOE, or even the zero optimizations will be subsumed within auto sharding search space. Another thing that I wanted to mention on the previous slide is that auto sharding is actually an open source fork of the Alpha project. This was also a research paper, and we'll have references at the end of the slide, so you can dive deeper into details if you'd like. So here we start getting a little bit into exactly how auto sharding works and how it shards an input HLO module, right? So we have a simple three-dimensional tensor on the left here with dimensions B, S, and H, and say that we want to shard or partition this tensor across 4 devices arranged in a 2x2 fashion. So that's the lower left colored 2x2 square you see. Now, given such a tensor and a mesh, there are multiple ways one can partition that tensor over that mesh, right? And those are enumerated. Some of those are enumerated there on the slide. So what auto sharding will do is, auto sharding will, for every input tensor in the HLO, start by first enumerating these potential sharding candidates or potential ways to shard these tensors for each of these tensors in the HLO module. Once that is done, next slide, please. Once the enumerating all the possible strategies is done, so that's the upper left portion of the problem formulation you see here. Once that is done, it will then move on to computing resharding costs for pairs of strategies between, say, across producer-consumer relationships, right? So assume that a producer is producing a tensor that needs to be consumed by its consumer. Depending on the shardings for the producer and the consumer, the resharding costs between them might be different. So auto sharding will enumerate all of those resharding costs for all of these possible strategies with the help of its cost model. And we'll go a little bit more into detail about the cost model later on. Once all of this enumeration is done, it will essentially pass on this problem to an ILP solver to minimize the total cost of the graph, subject to the constraint that the memory usage of the graph never go beyond a specified memory budget, right? We don't want our program to go out of HBM further downstream. Now, one thing that I want to mention here is that because we are interested in large models and models are getting larger and larger these days, the search space that auto sharding works with is often quite large, right? Typical LLM HLOs can have hundreds or even thousands of variables and constraints, and each of these tensors can have further potential sharding strategies for enumerated for those, right? So the search space is fairly large. Next slide, please. So again, just to get a simple sense of how large the search space is, right? Even if you assume a simple HLO with 256 instructions and 2 strategies for each, you have a 2 power 256 or 10 power 77 large search space. That's too large to actually explore one at a time. Now, while we do use an ILP solver, specifically the CPSAT solver that the Google OR tools team also releases publicly, and this solver will use a lot of fancy pruning techniques such as branch and bound, symmetry elimination, all of those things to get the search space smaller and to get to the optimal as fast as possible. Despite all of that, as said, auto sharding will increase compilation time, and we have seen models take several minutes to even a couple hours to run to completion. This is something that we are actively working towards, and I'll have a little bit more to say later in the slideshow. Next slide, please. So this is just one of the many strategies we use to sort of get over this problem of very large search space and slow solver times, right? This is a very simple strategy, but we have a lot more things that we do. So for example, this specific thing, right? We essentially want to use some domain knowledge to constrain the shardings of certain operators to reduce the search space, right? So here, intuitively, we can all say that for a simple HLO op, such as, say, an element-wise operation, we would ideally want its inputs and outputs to be sharded similarly, right? We don't want to perform all-gather communication just to add two tensors. That doesn't make sense. And so we can essentially use that domain knowledge to enforce that and tell the solver that, hey, all element-wise ops, they should have similar shardings as their operands. And that will prune away a lot of the search space for most of these element-wise ops, reduction ops, reshape ops, so on and so forth. And that helps us achieve more tractable compilation times. So now I want to move topics a little bit to talk about the cost model that we use and how we can tune auto sharding generally for other hardware backends. Right. So the cool thing about auto sharding is that hardware specificity in auto sharding is encapsulated as part of its cost model, and it is this cost model that it uses to estimate the communication cost of resharding tensors, which we referred to a couple slides ago, right? And to model this, auto sharding uses a fairly simple cost model. It's commonly referred to as alpha beta latency throughput cost model, where the cost of sending B bytes between two devices can be modeled as alpha plus beta into n, where alpha can be a stand-in for a latency term and beta can be a stand-in for your throughput term, right? And these two constants, alpha and beta, it's a fairly simple model, so we can actually tune these constants for any underlying hardware or hardware topology that is provided to us, right? So that's one of the things that we want to emphasize in this slide, that yeah, auto sharding is a fairly tunable pass that we can adapt to multiple hardware backends. Next slide, please. And one of the ways we can hypothesize doing that is what is shown here on the slide, right? So note that this is not an API support that we actually provide today, but we are actively working towards this, right? So one can imagine that we run an inbuilt provided script, which runs a few micro benchmarks, some communication patterns on new underlying hardware to come up with those two constants, alpha and beta, that I mentioned in the previous slide, right? And once we have such a model generated, cost model generated, we can easily pass it on to the next auto sharding run when we want to shard a given model on this new hardware, right? So this is a fairly simple strategy that we are hoping to work towards. And yeah, so please look out for this in next PyTorch XLA releases. Yeah, so now I want to talk a little bit about some of the next steps that we are thinking, next features we are hoping to work towards, right? So as you all know, auto sharding is released as an experimental feature on Cloud TPU in PyTorch XLA for single host machine learning models. And we are actively working to extending that to multi-host models as well. As I mentioned a couple slides ago, auto sharding is quite tunable to other hardware backends, and we want to support auto sharding on other hardware backends. And that sort of goes hand in hand with the customization of the cost model that's mentioned there. Another thing we recognize is that given the goal of auto sharding is to find reasonable shardings fast, we recognize that using auto sharding as part of a debug cycle is a potential use case. And so solver times are something that we are actively working to reduce. As I said, they can take several minutes to a few hours now. We do want to get it down to minutes, if not hours. That's something we are actively working towards. Yeah, so that would be the end of my talk. There's a few pointers here that you can go dive deep into if you'd like. I'll specifically point to the Alpha project and the corresponding research paper that you'll find on the website there, where you can find more details on exactly how the problem formulation and all of those things works. But yeah, that's the end of our talk, and we can take questions now.
What's the new Chardonnay that's coming? What's the difference between this versus that?
So, do you want to? So the way I understand it is that Chardonnay is a new API system and a new way of representing shardings across multiple different sharding solutions that we have, including GSPMD, auto sharding, even part IR was mentioned. So in some sense, think of it as a unifying API for these three sharding solutions.
They are also, yeah, it's unifying API, but at the same time, I think they are also working to merge some features from like different partitioner. But then for auto sharding, which here we have an alpha-based one, it's I don't think they mentioned anything about like merging the auto sharding algorithm into different one, but it's rather like SPFD plus Pattaya kind of. And I think it's important to highlight that auto sharding is a right now implemented in XLA as a separate pass. It doesn't replace SPFD partitioning, so it's like a back-to-back kind of sort of iterative steps that happen. Right? It doesn't. It's not one for the other, but they happen together. And sometimes auto sharding also falls back and relies on sharding propagation from SPMD.
Okay, so but the annotations are being inserted in the SPMD partitioner, or it's there, and then auto sharding takes these annotations and
no, auto sharding finds the sharding annotations, and then it passes that to the SPMD part. Yeah.
Okay.
Yeah. So
what is the main target for hardware for this auto sharding? Is that like you already have it for GPU or TPU or?
Yeah.
Yes, we have been working with TPUs all this while. But like I said, we are very actively working to get GPUs at least.
Okay.
So then the hardware must be pluggable to XLA ecosystem first.
Yes. I believe there's I believe the GPU is already able to do that, right? And another question is regarding your cost model. Is how did you guys have planned to improve the simple linear model to capture the complex interconnections for example, for different GPU have for PCIe and link, you have different bandwidths. I don't think the simple linear equation will be able to capture that, especially there will be some able to do the bandwidth sharing for different communities, right?
Yeah, so that's a good question. Currently, the one way we allow that to capture that is in the cost model. So like I mentioned the alpha beta cost model there. That was a little simplistic way of putting it. We do allow different values of alpha and beta for different dimensions of your device mesh.
Okay.
So that is one way we
Okay.
can. So for example, if all PCIe is on the X dimension while all NVLink is on the Y dimension, assuming PCIe is slower, then we can have a higher alpha or a higher beta for the X dimension, but not the Y dimension. So that's one way we can do that. Beyond that, we can also definitely look into making this equation itself more complicated if necessary, given that auto sharding itself uses this as a black box, and so we can replace the underlying cost model, including the formulation, easily if needed.
Thanks.
Question about the constraint algorithm itself. So do you guys assume that there's always a legal propagation of these sharding shapes, or do you actually, if let's say producer and consumer to have a conflicting thing, and they actually alter the HLO and then insert transpose and reshape to legalize it?
Yeah. So can you go to the cost model slide? Yeah, this one. No, sorry, no, sorry, not the cost model. I'm sorry. Yeah, this one. I'm sorry. Problem permutation slide. Yes. Yeah. So the mismatch or the conflicts that you're talking about will be captured by the resharding costs. So as you say, for example, right, if there are shardings for producer consumers where they are kind of mismatching or they don't really, you need to reshard or transpose a tensor, the cost of doing that resharding or communication or relayouting will be captured in those resharding costs. So the solver will know that this is a possible option, but that it has a certain cost. So it will choose that option only if it sort of minimizes the overall communication time.
But you don't you don't modify the original HLO graph, right? You still annotate with A and B with different.
Yes, the actual task of actually modifying the graph and inserting the transpose or all gather or whatever communication might be is done by another pass, which is called the SPMD partitioner pass.
Okay, that legalizes all the mismatch.
Yeah, that will essentially, yeah, do all of the insert these layout operations and all of those stuff. Yes, yes.
Gotcha.
Awesome. Any questions? Any other questions? If not, then we can all hang out in Mariposa Grove and get some coffee. Did everybody get the coffee with the little OpenXLA logo on top? That was super cute. All right, let's go downstairs. Thank you.
So I think they should be able to get the audio recording automatically.
The recording. Yes, I'll get it and then I'll edit it and then I'll put it on here.
So, and you will choose which one.
Fill out the survey though. Is that possible?
Right in this room?
Yeah.
Oh,
If you can, that'd be super.
yeah, let me find it.
It's in the know before you go.
Okay.
Yes, we want on divide by empty, then no latencies. And then when neither hardware is foundation tired, so we have to do this. Oh, I will install it.
那个非常性表里你能找到表的，所以
They just keep this on the hardware.
Yeah, I got.
I think we're at the same page.
Yeah, this index, huh? Yeah.
Is it working for you all? The morning
I-
before going?
Yeah, I'm asking my friend to send me that.
Know before you go. In the doc. It's so the email that I sent you.
Yeah.
On PyTorch.
You click on that link, tell me if it works.
During export, we export to the stable.
Okay, so you use PyTorch to export that model
Yes. .608, yes, exactly.
and then capture the stable HLO and then.
Well, we have you on chat too, don't we?
Running on the hardware.
You have a morning to close.
Are you on?
Happy to discuss what we can do to help with the application.
Yeah. So what have you did? Specifically.
So, frameworks and 3D ecosystem.
Oh, wow.
It's right here. So the know before you
That's-
go.
Yeah.
Did you?
Yeah, so right now we start picking up
The
the
tutorial survey.
highlight. Is the part we have written.